Hi, in previous video, we have seen VI characteristics of PN junction diode. In this video, we're going to see application of PN junction diode. So PN junction diode is used in a rectifier. Rectifier is circuit which is used to convert AC signal into DC signal. It is also used in communication circuits, in digital logic circuits, and clipper and clamper circuit. Today, we are going to focus on the clipper circuit. So clipper circuit, it is a circuit used to remove or clipping of some portion of given input signal. Means whatever the input signal given to the clipper circuit, we can clip off some portion of the input as per our requirement. There are two types of clipper circuit. One is series clipper and the another one is shunt clipper. This classification are based on the how we are connecting diode with the load. So there are two main components in the clipper circuit. One is diode and another is load resistor. So in series clipper circuit, diode is connected in series with the load. You see, we can connect input over here and diode is connected in series with the load resistor. In second type, that is the shunt clipper circuit, the diode D is connected parallel with the load resistor RL. So that is shunt clipper. Again, these two circuits are classified as negative clipper, positive clipper, and the clipper circuit with DC biasing voltage. This classification is based on what portion of input waveform we are clipping. Means if we are clipping negative portion of input cycle, then it is known as negative clipper circuit. If we are clipping or removing positive half cycle of the input signal, then it is known as positive clipper. We can add DC biasing voltage in the negative clipper as well as positive clipper. So before we'll start the shunt clipper, in this video we are focusing on the shunt clipper circuit. Just I'll explain how this diode act in the ideal case and the practical case. So this is the symbol of diode. It has two terminals, anode and cathode. Diode is unidirectional, so current flow only in the one direction when it is in the forward bias. So for forward bias, we connect anode terminal to the positive terminal of the battery and negative terminal of the battery is connected to the cathode terminal. So this way we can consider diode is working in the forward bias. So when diode is in forward bias, that time diode act as a closed switch. So in ideal case, that is ideal diode, we assume that when diode is in forward bias, that time it act as a closed switch. So the resistance offered by this diode is 0. It acts as a short circuit. In another language, we can say this act as a short circuit. But practically, there is some voltage drop across this diode. And that voltage drop is nothing but it is the barrier voltage between these two junctions. So therefore, in practically, we have this voltage drop of 0.7 if this diode is manufactured with the silicon material, then this diode voltage drop, which is known as VD, is 0.7. If it is germanium, then the drop or the voltage barrier is 0.3 volt. So this is the anode terminal and this is cathode terminal. So whenever we consider diode as an ideal case, in forward bias, it acts as a short circuit. and in practical case, it is act as a voltage. It is act as a voltage source which has the voltage drop of 0.7. In reverse bias, when diode is in reverse bias means we can change the diode polarity, supply polarity, and we can flip the diode. So here I'm just changing the supply polarity. So my anode terminal is connected to the negative terminal of the battery and positive terminal of the battery is connected to the cathode terminal. So this way we can make our diode in the reverse bias. So in reverse bias, in ideal case, diode act as a open switch. The resistance offered by this diode is infinite, very high resistance. So therefore, it acts as a open circuit or open switch. And practically also, it is offering very high resistance. So the resistance, reverse bias resistance is very high, infinite resistance. So this concept we use in the further explanation of shunt clipper. So we start with the first circuit, that is positive shunt clipper. Positive shunt clipper. Now in this we can see the diode D is connected, is parallel with the load resistor RL. So it is the shunt combination, parallel combination. Now we'll see how we will get the output. So suppose I'm considering this is my input, AC input signal, positive half cycle and negative half cycle is given to this diode, and we have to check the output at this two end. So for that, we consider some case, that is case 1 positive half cycle and case 2 negative half cycle. Consider case 1 during positive half cycle. So during positive half cycle, what happened? The polarity, it is positive. So it is plus minus VI voltage applying to the clipper circuit. So because we can see this anode terminal is connected to the positive terminal and cathode terminal is connected to the negative terminal. So this diode is act as a short circuit. First we consider the ideal case. So in ideal case, this diode act as a short circuit because diode is in forward bias. So when this diode is in forward bias, I'll redraw the circuit. Act as a short circuit, the remaining part of the circuit, and we are applying positive half cycle. So you can see at the output, it is already shorted. Your input signal is shorted to the ground signal. So there will be no output. The output is 0. So output V0 is the output and Vi is the input. So Vi value is 0. But if I consider practical diode, what happened with the practical diode? Practically, it will replace with the voltage drop of 0.7. So if I redraw the circuit, I have to draw the voltage of 0.7. So at the output, I'll get 0.7 voltage. So when I applying positive half cycle to this circuit, practically I'll get 0.7. This value is 0.7. Till this diode is in the off stage, because to turn on the diode or to make the diode in the conduction, the minimum voltage should be 0.7. So till that the diode is act as an open circuit. So whatever the input you are giving, you will get at the output. So you will get this curve, and when the diode is in the forward bias, it will give the constant voltage of 0.7. Now we'll see case 2, that is negative half cycle. Case 2, during negative half cycle. Again, in ideal case, the diode act as a open circuit, because when we are applying negative cycle, the polarity at the input side is minus and plus. So diode is in the reverse bias. So it acts as a open circuit. Open circuit. If I'm checking the output at this end, what I'll get? My output voltage is the voltage drop across RL divided by the total resistor R1 plus RL into input. Now here we select the value of RL is very high. So practically when I'm performing this practical, I'll take RL as 100K and R1 is equal to 1 kilo ohms. So if I solve this, so approximately I'm substituting the value of RL. RL is very high. So this term R1 plus RL is around RL. So it will get cancelled, and approximately your V0 is equal to Vi. So it states that whatever the input you are giving at the output, you will get the same. So if I am applying negative half cycle, negative signal, my input is negative, so at the output I'll get same negative side. Okay, my output is equal, this is my output, this is my input, so my output is equal to input. Same thing is happen with the practical diode also, because practically also it is offering very high resistance, so it is act as an open circuit and you will get same waveform. So if I draw the complete input and output waveform, this is my input waveform, this is the T. I'm plotting the waveform with respect to time. Positive half cycle, negative half cycle. I'm considering the amplitude 2 volt positive and minus 2 volt. So it is 4 volt peak to peak signal I'm giving as a input. So what I'll get at the output? Just I'm taking the reference. So during positive half cycle, first I'm plotting for ideal diode. So ideally, when it is positive cycle, then it acts as a short circuit and my output is equal to 0. So I'll get 0 output, straight line. And at the negative cycle, we'll get same signal. Output is equal to input. So if I take the magnitude, it is around 2 volt. This is for ideal. If I want to plot practical, output for practical diode. So what will happen with the practical diode? During positive half cycle, we'll get voltage drop of 0.7. This voltage is 0.7 volt, and during negative half cycle, we'll get same as input signal. So this is the explanation about the positive clipper, positive shunt. Why it is known as positive shunt? Because it is clipping of the positive cycle. If you see the output waveform, this is the input positive half cycle and this is the negative half cycle. And at the output, your positive half cycle is clipped off, is removed. So it is known as positive clipper. And the load resistor RL is connected in parallel with the diode. That's why it is known as shunt clipper. Similarly, we can plot for negative shunt clipper. So same way, we can use shunt negative clipper. For shunt negative, you can see just I have flipped the diode. So now when we consider the input signal, for input signal positive half cycle, the voltage is plus minus and diode is in reverse bias. This reverse bias condition is for the positive half cycle. So in positive half cycle, diode, ideal diode act as an open circuit. So therefore, there is no output. Output is equal to, almost we are getting output as a VI, because diode is act as an open circuit. So open circuit means just voltage drop across this RL. So it is approximately input voltage. So whatever the input we are getting, that same input will get at the output also. Okay. And during negative half cycle, the polarity will change to minus and plus. So now positive terminal is connected to the anode terminal. Therefore, diode is in the forward bias. Now when the diode is forward bias, it acts as a closed switch. It is completely closed and therefore output is equal to 0. There is no output at the negative half cycle. Output is 0. So you can see the negative half cycle is clipped off or removed from the input. So similarly, we can see for the non-ideal diode. Non-ideal diode means practical diode. For practical diode, we have to just consider the voltage drop of 0.7 volt when it is in the negative half cycle. For positive half cycle, diode is act as an open circuit. So we'll get the same output is same as input. And during negative half cycle, the voltage drop across diode is 0.7. So that can be seen over here. Now in this, with addition with the biasing voltage, we can add the biasing also. So first we'll see what happens if we connect both the diode together. So that is known as slicer circuit. So this slicer circuit without biasing. So just we have considered two diode. So D1, if you see this connection wise, so this is in the forward direction and D2 is in reverse direction. So during positive half cycle, when we are applying positive half cycle, that time D1 is on, which will act as a open circuit, or which is act as a short circuit in ideal case, and in practical case it act as a source of 0.7 volt, voltage drop of 0.7. And during negative half cycle, D1 is off but D2 is on. D2 is on for negative half cycle and it will give a voltage drop of 0.7. So at the output you can see this is the 0.7 drop because of diode D1 is on and D2 is off. And this voltage at the negative half cycle is due to the diode D2 because D1 is off in this case. So if I add biasing voltage, so biasing voltage means external DC supply. So I'm adding this voltage source in series with the diode. So if you see the polarity, this is positive and this is negative. So I'm adding positive voltage. So whatever the VB voltage I'm applying, that will get added. So this is the circuit for positive shunt clipper. Diode is connected in shunt, that is parallel, and it is positive. It is clipping the positive half cycle. So in previously we have seen that we are getting the voltage drop of 0.7 during positive half cycle, but we have added the voltage source, so at the output you get 0.7 plus whatever the supply voltage VB. So if I am adding VB as a 1 volt, so my output V0 is 1.7 volt. So here I'll get 1.7 volt. For negative biasing clipper, the connection wise, this is negative shunt clipper circuit, and I have added the biasing voltage VB. So it is clipping off the negative cycle, but because we have added VB voltage, so it is negative voltage. So totally it is minus VI, whatever the input, VD voltage, that is 0.7 voltage, then minus supplied voltage, that is VB. So again VB is 1 volt, that is minus because we are connecting polarity negative and positive. So it is minus 1 volt. So negatively 1.7 volt. So here it is, if I plot 0, then it is minus 1.7. I can add these two signals also. Like we have seen the slicer without biasing. So we can add these two with the biasing voltage. So D1 is connected to the V1 in series and D2 is connected in with the V2. So overall output, if I am applying the input signal for positive half cycle, D1 is on and D2 is off. So at the output, I'll get V0 is equal to voltage drop across D1 plus V1 voltage. So here again I am considering V1 as a 1 volt. So the value of V0 is 1.7 volt. So till 1.7 I'll get the output. During negative half cycle. During negative half cycle, now D1 is off and D2 is on. So output is due to diode D2 voltage and it is negative. So negative voltage V2. So again I am considering V2 as minus 1. So the overall output is minus 0.7 because why I am writing minus? Because it is negative at the below 0 and minus 1 volt. So at the output I'll get minus 1.7 volt. Minus 1.7. So till I'll get the output. So at the output, we are clipping both input and output cycle. So that's why this circuit is known as slicer. It is slicing your input signal. Thank you.